we are going to discuss about stereoscopic imaging or 3D vision. Now let's proceed. Recovering 3D image from images. How can we automatically compute 3D geometry from image? What cues in the image provide 3D information? That's the basic of it. Now visual cues for 3D images are shading, as you can see here, texture, focus, motion. And others are highlights, shadows, silhouette, inter-reflection, symmetry, light polarization, and many more. Say from x equal to shading, texture, focus, motion, and etc. We will focus on the motion cue for these few slides. Now here two camera points are, or viewpoints most to be correct, are set up left and right to determine the depth of the object. Now this is our human eye. We are going to observe two images here, and the small angle is for the farther distance and the larger angle is for the smaller distance. The C is for human eye is 63.5 mm, that's millimeter, and this is how you see, and it shouldn't lie on the focal point or shouldn't get crisscrossed with the focal points, because then it will create the object will get vanished from your view side. As you can see in the earlier physics experimentations were there, where you kept your finger here and this finger would get vanished from your perspective, and that's how it is explained. Now D equal to C by 2 tan A by 2. That from binocular disparity. Now binocular stereo, where we use two cameras to determine the depth and we plot it. This is for it. Abraham Lincoln. We can use these two images, have a 3D image of this person, or most honorably Abraham Lincoln. What can we determine about the size of the object, the distance of the object from the camera? For 2D and 1D we can't determine anything. For 3D we can determine exactly what is the size of the object, because we can have scaling. For 2D also we can have the size of the object, only but the length and the breadth, not the depth. And the distance of the object can be well defined by the depth configuration of 3D images. Now these are some of the problems which are faced. Now 3D shape from X, shading, silhouette, texture, stereo, light stripping, motion. Now today we are going to only discuss about stereo. Light stripping is going to be there in these slides, but we are only concerned about stereo. Now perspective imaging modeling 1D. For 1D we are only going to observe a line or a point. For 2D we can simply observe a square, rectangle, circle, or any other 2D object. Here, as we earlier said, the length of the breadth and the length can be determined possibly greatly, but the depth cannot be determined of a 3D object. Now for that we need a 3D vision. So for 3D stereo we have left image, right image, and D equal to X left minus X right. It's similar to 2D image itself, where we consider the focal point X and XC and ZC. Now depth perception from stereo simple method, parallel optic axis. Here we have considered left and right cameras and considered the baseline, as you can correlate it with the earlier image of human eye, the distance C, in the image plane Z. Focal F is the focal length, or simply said, and XL, XR are the points where they cut it. Now Z by F equal to X by XL, Z by F equal to X minus B by XR, Z by F equal to Y by YL equal to Y by YR. Y-axis is perpendicular to the page. Let's consider the page which is going to be observed. And for general notification, I should suggest you to consider L as left and R as right. Now resultant depth calculation for stereo camera with parallel optic axis, focal length F. and baseline B corresponding images point y1 x1 y1 and xr yr. Disparity D y z equal to f into b by xl minus xr equal to y f into b by d. X equal to xl into z by f or b plus xr into z by f. Y equal to yl into z by f or yr into z by f. This method of determining depth from disparity is called triangulation. As you can see, from perspective projection we are getting the same kind of result. XL by f equal to x plus b by 2 by z, xr by f equal to x minus b2 by z, yl by f equal to yr by f equal to y by z. Now we are going to observe a scenery from the two cameras or two eyes or whatever, and we are going to determine it. Now disparity and depth, we have extended the formula. Capital X equal to B into XL plus XR by 2 into XL minus XR. Y equal to B into YL plus YR by 2 into XL minus XR. Z equal to BF by XL minus XR. D equal to XL minus XR is the disparity between corresponding left and right image point. Inverse is proportional to depth. Disparity increases with baseline. This is the divergence. Here the uncertainty of the scene point occurs if this B distance is shorter. Now, as we increase it or we keep it on an angle, we clearly see the uncertainty of the scene point greatly decreases. It is preferred. That's why I can, for our eye it is 63.5. For the God's grace we can see everything properly. Field of view decreases with increase in baseline inversions. Accuracy increases with baseline inversions. Binocular stereo means from 2 points how we are going to have it. Triangulation. The principle we just discussed requires calibration, point correspondence. Now for some very specific application it can't be solved for those specific kind of images. Example, windshield of a car. Now 3 main matching methods are cross correlation with a small window, symbolic feature matching usually using segments and columns using the newer interest operator, that is shift. Epipolar plane is another technique of which you can have it. Epipolar geometry. Here also we consider two cameras, C1 and C2, and we are going to observe this P point and we are going to determine its depth, length, breadth, everything. Now these are the other methods. Now basically some of this translation, scaling and rotations are basically required for getting proper image, because you can't have Taj Mahal in your screen totally fitting it as it's too big. So proper scaling, rotation and translation is required for the image so that a proper image can be obtained from it. Now these are the other methods and the recent research is going on. This is stereo rectification. As observed, we have taken two images and we have just rotated it, and then we would be combining it to get a 3D image of this puppet and that object inside that cube. The epipolar line method is being here shown. The stereo results, scenery, the ground truth. There are the two images. It's a 2D image. Now the ground truth is the window based matching and best window size, ground truth. These are taken from book of FL, International Conference on Computer Vision, September 1999. input image 1 of 2, depth map, 3D rendering. We have got a 3D image out of it. Left image, right image, depth map. We have got a depth effect of it. And when we map it, we get a 3D image of it. And if a proper the criteria are met, we can have a 3D image from our human eyes itself. Similarly, in train scanning and structured lighting, that's the light stripping method. So basically, the applications here are for medical purposes, where the operations are now been done through 3D imaging itself, and for entertainment purposes, as today you can see many 3D pictures are coming out, and lots of other cases like 3D models are being created before creating the base main object itself. So it is very much useful, but the only thing is that for some reason these images for the timing and holograms are today's revolutionary things. As you can see in Yokohama recently, they have created an event for Pokemon. They have created 3D image for Pikachu and Eevee. So it was kind of nice, and still there. You can have a search over it. Now, basic problem today we face are basic headaches when we wear those spectacles and all, because till now there is no other method to have a 3D image without wearing those spectacles and other things, except for holograms itself. It was it, and today it is getting embedded into our system greatly. Now, because of 3D imaging itself, we have got 3D printing possible. So thanks. I would be ending my video with this.